This is chapter 16 on energy changes and thermochemistry. Um, First slide I want to start off today talking about is a slide that's basically going to kind of tell us what kind of processes, what kind of things that happen require energy changes. And we're talking about energy changes, as we talked about before. We're talking about calculating things like delta H, change in enthalpy. Remember, at this point, we're only going to be dealing with um, constant pressure processes, things that happen at constant pressure. In other words, things that happen out in the open so that they're not all closed off. You may have seen a video before that talked about the bomb calorimeter, and that's when things are at constant volume, which is constant pressure. And that also occurs, but we're not going to deal with it too much. So we have our energy changing processes, delta H. There's delta H. And we get a delta H, a change in temperature, when one of these three processes occurs. Either there's a temperature change, like you heat up a cup of water or you cool down something in the refrigerator. So if there's a temperature change, there's a delta H, and therefore there's a Q involved. Remember, Q is heat and how much heat has either come into the system or gone out of the system. So whenever something doesn't change what it is, but it changes temperature, we can calculate a delta H. Same thing with chemical reactions. In the last slideshow, we talked a little bit about that. So chemical reactions can also calculate. We can also calculate delta H because energy is coming and going between the reactants and the products, or at least coming out of or into the reactants to turn them into products. And we'll go ahead and review that in just a little bit. And the last one are phase changes. Phase changes, I think, are famously familiar. If you take an ice cube, you put it on the table, it starts to melt. But it starts to melt because it's starting to get heat or energy from the atmosphere. And this will happen if the temperature is above its melting point. So we're actually going to need energy in order to turn the solid water into liquid water. Same thing when you boil something. You're going to have to warm it up to its boiling point. And once it's at this boiling point, you still need to put energy in. If you get water to 100 degrees Celsius, you stop there. It doesn't all magically turn into gas and steam. You have to, once it's at 100 degrees Celsius, you have to keep heating it, or at least keep putting in energy, keep putting in heat until while it continues to turn from a liquid to a gas. Okay, so those are the three processes that will make energy go in and out of a system. Those are the three processes you can calculate a delta H for. We've already seen this before. Here you have a chemical reaction, and when there's a chemical reaction, there is a delta H associated with it. This is what we call a thermochemical equation. You'll always hear the term thermochemical equation. Oh, and it sounds so ominous and sounds so serious. This is a thermochemical equation because it's a chemical equation that has energy related to it. Right? So you got a chemical reaction right here, and it tells you how much energy is going to be given off or taken in, depending on the nature of the reaction. So we'll talk a little bit more about it in just a little bit, or at least how we would use this in a problem. We'll do some sample problems, how you would use the thermochemical equation. Really, just a chemical equation with delta H equals to that, and that's related to chemical reaction. And this delta H here, what it represents is the difference between the reactants and the products. If the reactants have more energy than the products, or I should say enthalpy in this case, that means that the products aren't going to need as much, so the excess can be given off. And that negative right here means that it's losing. So you had these chemicals, they had this much enthalpy. Then they got turned into another chemical or chemicals, depending on the reaction. And when you jump from here to here, well, you didn't need as much energy, so that extra energy was given off. And that's where you have the minus 285 kilojoules per mole. The enthalpy of the products minus the enthalpy of the reactants, then you have a negative number when the products have less than the reactants. And then this is an exothermic reaction. Exothermic meaning energy is being given off. In an endothermic reaction, I said this was exo, right? I was being distracted by which button was working, which one was it? But this is an exothermic reaction. The delta H is negative. An endothermic reaction is when um, the reactants have less energy than the product. So you're going to need more energy. Not only are you going to turn the reactants into products, but then you have to put extra energy in. And so the chemicals suck in extra energy from from the atmosphere, from the surroundings around them, in order to get enough energy to turn into the product. In this case, CO2 and H2O have less energy than CH4 and O2. So we not only have to turn the reactants into products, but we also have to suck energy in from the outside, from the surroundings. Okay. Now, that's the second. Well, that was the second bullet point on those three, right? We talked about temperature changes in previous reactions. Now we calculate Qs, and those Qs are also going to be delta H's because it's a constant pressure. These things are happening at constant pressure because why? Because we said they are. That last one was chemical reactions. The third one are phase changes, or another term for them are energies of transformation. And energies of transformation are when substances change from one state of matter to another. There are energy changes associated with these phase transitions. You have to put energy in to turn to get something to melt, from a solid thing into a liquid, whether it be ice to water or whether it be a solid piece of chocolate, get it to melt to liquid chocolate. So during these phase transitions, the temperature of a substance stays constant. We don't get temperature. You warm up some water, and the temperature starts going up. But during a phase transition, the temperature stays constant while the transition is taking place. But that doesn't mean that energy is not still being put in there. Okay, so during the phase transitions, the temperature of a substance stays constant while the transition takes place. These transitions take place at the melting or freezing point and the boiling point of the substance. Okay. There's this thing called a heating curve. And the heating curve basically kind of shows you what happens as you put energy in it. So on the x-axis, we're going to have time. You're heating something up. You can also put down Q, delta H. Because as time goes along, if you're heating something up, you're adding heat to it. And the y-axis is temperature. So that shows you how temperature behaves as time goes along. Start off at a certain, whatever temperature this might be. Let's say this is water, just because it's easier for us to kind of, we know some things about water, its melting point and its boiling point. So we can get an idea. We'll get an idea of what some of these values might be. Remember that the melting point or freezing point of water is 0 degrees Celsius. So here would be 0 degrees Celsius. And the boiling point is 100 degrees Celsius. So here's where the liquid and gas come in. This is the boiling point. And so this is the boiling point right here. So this would be your boiling point right here. Whatever the temperature, this is the boiling point. Whatever temperature here is your freezing point. So this has got to be negative in Celsius, right? This is 0. So anything below is negative. Let's say it starts off at, I don't know, negative, looking at these, maybe they're not to scale, but let's say it starts at like negative 110 degrees. You have ice at negative 110 degrees, and you start heating it up consistently. Its temperature is going to go up. It's going to go up. And the slope of this line is going to be based on the specific heat capacity of the substance. Till you get to the melting point. And then once you get to the melting point, notice how this flattens out. What this flattening is telling you is that you're still putting in heat. This heat, if you're going from left to right on this graph, you're putting in heat over a given amount of time. However, because it's flat, that means the temperature is not rising. That's because the solid is turning to liquid. So this flat area right here is melting. Temperature does not change, but we're still putting heat in. Once you get the whole thing to melt, and it doesn't exactly work that way, but theoretically you can kind of work it this way. Once the whole thing is, so we assume that once the whole sample of whatever you've got has melted, now it's all liquid. At this point, it was all solid. Then it became more and more liquid until you got to this point. Now it's all liquid. We continue heating. Now the temperature starts going up again until you get to this point right here, where once again we got a flat area because we've hit the boiling point where the liquid starts turning to gas. Now, the boiling point usually is got a larger flat area because it's harder to turn a liquid to gas than a solid to a liquid. Notice that this was a flat area right here. This one's much wider because it takes more energy. It's still the same sample size. You know, if this was 100 grams, it's still 100 grams. Here you're turning 100 grams of solid into 100 grams of liquid. Here you're turning 100 grams of liquid to 100 grams of gas. But um, it's going to take longer to do it because it takes more energy than it turns to gas. So here at this point, we've got it all liquid. By this time, it's all gas. Then once it's all gas, it continues to heat. So that's what your typical heating curve is going to show you. Okay, the temperature increase for the solid. That's where the first chunk of energy goes into, and it's on the y-axis. You can show it's this is how much energy it takes to warm this sample from here to this temperature. Then this is how much energy it takes to take this whole sample and melt it. And then this is how much from here to here, this segment is how much energy it takes to warm it up. And this segment right here is how much energy it takes to vaporize it, boil it, and et cetera and so on. Okay? So that's how a heating curve works. As I said, the heating curve for water would have the boiling point of 100 here and the freezing point of 0 here. And that's generally how it works. The shapes of these tend to be the same. It's just where is the boiling point, and where is the melting point? Okay, where does that go? And also the slopes vary. Okay, so you can kind of see how it works for water. Here I have this next slide right here. I have the heating curve for another substance. This one's acetic acid. And acetic acid is an acid, and it has a little different. Well, we know it normally is liquid at room temperature, but it also has all three phases. Its melting point is about 16 degrees Celsius, as you can see right here, and its boiling point is about 118 degrees Celsius. So notice it's the same shape. You know, it goes up, flattens, goes up, flattens, and goes up. Right, and the only difference is at what temperature that occurs. For water, the flattening of the melting point here would have been right here, and the flattening of this transition over here would have been right over there. Okay, but the basic shape is the same, and so that's what's going to change. These flat areas have specific names, and we're going to talk about those right now. This one is called the heat of fusion. How much energy it takes to get from here to here is the heat of fusion, and how much energy it takes to get from here to here is the heat of vaporization. And so we'll talk about those in the upcoming slides. What is the heat of fusion? Well, the heat of fusion, which can be represented by a delta H with a FUS subscript, fusion, is the energy required to melt a substance at the normal melting point. It is given per mole or per gram of substance. So how many joules or how many kilojoules does it take to melt 1 mole or 1 gram of a substance? You have to kind of look at your units and see, are you talking about moles or grams? For water, remember, there's 18 grams per mole. So your heat of fusion in terms of joules per mole is going to be 18 times bigger than your heat of fusion in terms of joules per gram. Sometimes we use joules per mole, sometimes we use joules per gram, depending on what quantity variable we have. Yeah, so for water, here's an example. The heat of fusion is 6.02 kilojoules per mole. What that means is that if you have 1 mole of water and it is in ice form at 0 degrees Celsius, it's going to take 6.02 kilojoules to melt it. If you have 1 gram of water, the heat of fusion in terms of joules per gram is 334 joules per gram. One thing to note, this is kilojoules. So this is thousands of joules, 6,020 joules per mole. This is 334 joules per gram. This number is about 18 times bigger than this one because, once again, water is 18 grams per mole. Now, this is when your substance melts. If you want to have what's called the heat of freezing, which a lot of people don't call it that, they just call it the negative heat of heat of fusion. But if you want to freeze a mole of water, all you do is take the negative, because freezing a mole of water is the opposite process of melting a mole of water. So if it takes 6.02 kilojoules to melt a mole of water, and you have to put that in, you have to put energy in to get the solid to turn to liquid. In order to freeze a mole of water, you have to take out 6.02 kilojoules. You put in the freezer, and the freezer is cold, and so the energy is going to go from the water out. And after 6.02 kilojoules have gone out of it, then now our liquid is turned into a solid. Okay, so you can call it the heat of freezing. Nobody really does that. It's just the negative of the heat of the fusion. And here I have energy diagrams to show what that is. You start off with we can see it as a chemical equation, although what chemical equation has is starting off with solid water turning into liquid water. The H for this process is 6.02 kilojoules per mole. And what that tells you is that, well, liquid water has an enthalpy that is 6.02 kilojoules more than solid water. So in order to get from here to here, you have to put in those 6 kilojoules. Notice this is positive because you have to put energy in to get it to go to the a higher energy level. Both of these are water, but they're in different states of matter. So you know that a liquid has the particles moving around, solid has them standing still. So they're in a different state of energy, even though they're the same substance. If you want to do the opposite, instead of melting, you want to freeze, you just do the opposite. Liquid turning into solid, the delta H is the negative. Notice the value is the same as before. Before was 6.02 positive. It was a positive 6.02. Here now it's a negative 6.02. And now that liquid is turning into solid. And remember, the solid has less enthalpy than the liquid does. Okay. Every state of matter of the same substance, it's going to have a different amount of enthalpy. You don't expect ice and steam to have the same amount of energy in them, right? I mean, they're both water, but steam is particles that are flying around all individually, and the liquid water is all kind of sitting there. The other transformation, the other phase change is from liquid to gas, and we call the amount of energy it takes to go from liquid to gas, we call that heat of vaporization. Heat of vaporization represented by delta H subscript VAP. So heat of fusion is delta H FUS. Heat of vaporization is delta H VAP. And it's the energy required to boil a substance at the normal boiling point. It is given per mole or gram of substance. For water, the heat of vaporization is 40.7 kilojoules per mole. That means 1 mole of water takes 40.7 kilojoules to vaporize. Once again, notice that this number here is much bigger than the other one. The heat of fusion for water was 6.02. This one is 40.7. So it's still 1 mole of water being turned from a liquid to a gas, but it takes much more energy to do that than 1 mole of solid water turned into 1 mole of liquid water. If we turn this into per gram, it turns out it's 2.26 kilojoules per gram. Remember, these are in kilojoules. That's thousands of joules at a time. Calculate the energy required to condense a substance, you use the negative of the heat of vaporization. Some people call it the heat of condensation. That one's probably used more than heat of freezing, but it's still not used as much. It's just the negative heat of vaporization. So whenever you want to figure out how to condense, because remember, condensation is the opposite of vaporization. Turn a gas into a liquid, you condense it. So the heat of condensation is a term that can be used. But people just go, oh, okay, what's the heat of vaporization? Since we're condensing instead of vaporizing, we're just going to use the negative heat of vaporization. And just as I showed you earlier, same idea here. Turn a what this represents is when we talk about heat of vaporization, it's a liquid turning into a gas, and this is how much energy it takes per mole or per gram, what you're given. And that just tells you that a mole of the gas of water has 40.7 kilojoules of energy more than a mole of liquid water. It's going to take 40.7 kilojoules extra to get it up there. Okay. Now I'm going to do some sample problems where you can be using these thermochemical equations. And technically, these are energies of transformation, but you can think of them as thermochemical equations. We'll use them for chemical reactions, and we'll also use them for heat of vaporizations, just to show you kind of how to use them. Okay, so thanks for listening, and we'll get you on the next slide. Bye.